While we're looking at hyperbolas, it seems appropriate to talk about variation. So our textbook introduces this concept now. Now we're comparing here direct and inverse variation. And instead of variation, sometimes the word proportion is used, because really all we're doing here is we're looking at how x and y might change in proportion with each other. So these two situations look entirely different. This one is a linear graph, and this one looks like an arm of our hyperbola, but it's just the arm that belongs in the positive quadrant. So what do these two things have in common? Well, they're surprisingly often related to each other, and we'll look at a simple example in a moment that will show you that. But what we can see is that in this linear graph, we can say that as x increases, y increases directly. Now, it's directly related, like that rate of increase here is really directly related just to whatever the gradient is. And you'll see here that the basic form of a straight line is y equals something x plus something. Now there's no plus something here because the y-intercept is 0, but we could say that k is the gradient. So it's really telling us how fast y is going up compared to x. Does that make sense? We call k here the constant of variation, or the constant of proportion, because it really, in this situation, is governing just how quickly y goes up compared to x. But I think you can see here that it's a very predictable climb. And as x goes up, y goes up in that very predictable way. They're moving together. And that's quite the opposite of inverse variation, also called inverse proportion, where as x increases, y decreases, but it's not a linear decrease. In fact, it's that curve that we see on one arm of a hyperbola. So it should be no surprise then that the formula is the formula for a hyperbola. Y equals something over x, where that something, instead of calling it a this time, we're just calling it k, because k is our constant of variation, or our constant of proportion. Now, the value of k will tell us just how quickly this y value is dropping as x is increasing. So it pretty much governs the shape of the curve, because we know that different k values would make the curve sit out here more or sit in here more, but it's going to have that same basic shape. Now, an easy way to remember which one is which, this one is climbing directly as the other one climbs. Whereas this one, the word inverse actually is often applied to fractions. Now, you've probably seen the word reciprocal. If you take the reciprocal of something, you flip it upside down, or you find the inverse of it. Inverses are all about having our x on the bottom instead of the top. So to me, if we compare these two formulae, we can see they've both got y equals, and they've both got a k and an x, but here we're multiplying by the x, and here we're dividing by the x. So we're taking the inverse operation of multiplying by x. Now, a really simple example that I think nicely illustrates how direct and inverse variation can happen in a situation that's seemingly really simple. Let's just take the area of a rectangle. There couldn't be much simpler maths to look at here. We know that area equals base times the height. So let's compare the relationship between base, height, and area of this rectangle when we do two things. We're going to either keep the height constant, but allow the area and the base to vary, or if we keep the area constant and we allow the base and the height to vary. How would we graph those things? Well, if we're graphing area and we're allowed to change the base, it makes sense to look at lots of different base measurements that we could have and consider how the area would change. Now, if the height's staying the same all the time, as the base gets longer and longer and longer, we are going to take a different number and multiply it by h. So in fact, what we're going to have here is direct variation, where as the base gets bigger, the area gets bigger, and it's going to go up in a linear fashion like that. Whereas if we keep the area a constant, now to imagine this, pick a number that you know lots of factors of, say 20. If we said, right, the area of this rectangle is going to stay at 20 centimeters squared, but you're allowed to vary the base and the height as you like, it makes sense then that the base and the height have to be two numbers that multiply together to make 20. And so if you graph the base and think of all of the different values that you could use, and you graph the height, then what you're going to have is a small base is going to have a really tall height to make that area equal 20, whereas a really large base is going to have a really short height to keep the area at 20. So here we end up with that hyperbolic branch situation. Now that makes sense when we remember that if the area equals the base times the height, then if we're graphing the height, and we're saying h is equal to something, then we could divide both sides by the base, and we'd have to say that height is equal to area over base. So if we fixed the area at, say, 20 for this one, it could be anything, I just picked a random number, then what we've got is this situation. And that shows us why it's a hyperbola and how those basic things can interact very differently depending on which thing we're allowed to vary and which thing we keep as a constant.